Welcome to this video on the power method. The power method is the very first numerical method we will study for finding eigenvalues. It is quite a simple method and it will only give us one eigenvalue and one eigenvector. So we will address it in quite some detail and also look at the convergence speed, because more advanced numerical methods are in a sense generalizations of the power method. So we will study it in a kind of basic form, which is the topic of this video, and then we will try to speed it up in future videos and also extend it to find more than one eigenvalue at a time. So let's look at an outline of this video. So what we'll be considering is the power method. We'll do some first experiments on the power method in MATLAB. Then we will look at Rayleigh quotients, and that will lead to a kind of scaling of the algorithm. I will present an error estimate and then I will present the method with scaling. So let's have a look. First, a couple of characteristics. So just things, properties of the power method before we actually study it. So it computes one eigenvalue eigenvector pair. So during performing the method will give us the eigenvalue, one of the eigenvalues, plus the corresponding eigenvector. Now, if you have a matrix in Rn times n, so a square n by n matrix, then we will assume that we have the eigenvalues lambda 1 up to lambda n, and we will call u 1 up to n the corresponding eigenvectors. And what I will assume, just for presenting the method to make it a little bit easier, is that all the eigenvectors are independent. Of course, that's not necessarily true, but we will assume it here. So if you would choose any vector in Rn, n equal to 0, then what we could do is, since we have independent eigenvectors and we have n of them, they form a basis of Rn. So I can write any vector in Rn, also the 0 vector, but I'm not interested in the 0 vector. So I can write any vector x0 as a linear combination of the eigenvectors. Now, if you would next perform this iteration, so what I'm going to do is I'm going to apply the matrix A to the vector x0, that gives me x1. Then I do A times x1, that gives me x2, and so on. So basically what I'm computing here is that I'm starting with x0, then I compute x1, which is a x0, and then I compute a squared x0, and so on. So I get higher and higher powers of the matrix A times my starting vector x0. Let's see what happens here. So I am going to be using this example a number of times. So I have a matrix, a 5 by 5 matrix with some integer numbers apparently. I am going to start the iteration, so that's my x0 that you see here, and x0 is 1, 1, 1, 1, 1. So it is the vector of appropriate length, length 5, which has ones. And here apparently I do 5 iterations. So I compute a times x and I do that 5 times. So if you do that, you get in iteration 1, you have the vector with components, well, what you see here, what is it? So 20, and the second component is 26 and 24, 19 and 11. Then we do another iteration and another one and another one. And what you see, if you just look at the exponents here, you see that the numbers get bigger and bigger. So the components of the exercise become very large, and it's hard to see here anything. And this can also lead to problems if the numbers get very big. So this is not very nice. So let's introduce a bit of scaling here. So I'm going to choose the same z, but now I'm going to divide it by its norm. So that means that the new z, so the z that I've computed here, has length 1 in the 2 norm. The standard norm in MATLAB is a 2 norm. And then in every iteration step, during the iteration, I'm also going to divide z by its norm. Let's see what happens here with the z's. So what you see here is that the z's converge, because you see, if you look at the first column, that's the first component of the z vector, you see that it appears to go to some limit value, and the same holds true for the other entries of the z vector too. If you take more, 5 is of course a very limited number. If you take more iterations, you will see that there is convergence here to a fixed vector. To which vector? That could be the question. So let's do a little bit of analysis now. So let's see if we can predict using just the theory, the linear algebra, what's going to happen here. So I have my starting vector, and I'm going to apply a number of times. And what I do here now is that I say, well, if you apply a number of times, you could directly apply it to the sum, and then you can move the matrix to the vector ui. So then we have this here. But the uj here is an eigenvector. So if you apply your matrix a times, a to the power I times uj, you get lambda j to the power I times uj. So the corresponding eigenvalue to the same power as you had the matrix there. And now let's assume that I am going to order the eigenvalues. So lambda 1 is going to be the biggest one of all of them in absolute value. So I'm going to assume that the absolute value of lambda 1 is really bigger than lambda 2, and then bigger equals, so I sort the rest of them too, but the rest I'm not really interested in. I just want lambda 1 to be really bigger in absolute value than the rest of the bunch. Then if I write the sum here for xi, if I split off the first term, and then I let the sum begin by j equals 2, so the first term I write separately, and then the rest, that's basically what it says here. And because this lambda 1 is bigger than the rest, I'm going to pull that in front of the whole sum. So I put brackets here, and everything within, well, we still have this beta 1 times u1. And then in the sum here, the rest of the terms, we get lambda j over lambda 1 to the power I. Now, lambda 1 is really bigger. So what that means is that if you would take the absolute value of lambda j over lambda 1, that it's less than 1. And that means that all of these terms, if you take sufficiently many iterations, it gets here to the power I, they're going to 0. So if you let I go to infinity, then you see that apparently the x1s converge to lambda 1 to the power I times beta 1 times u1. So what it means is that u1 is the eigenvector that corresponds to lambda 1. And this lambda 1, since it's the biggest one, we will call that the dominant eigenvalue. Dominant eigenvalue. And it's dominant. The reason is basically what you see here, the derivation on this slide. If you take more and more iterations, it's the only one that you will still see. You only see the first eigenvector, the eigenvector corresponding to lambda 1, and the rest goes to 0. So the vectors xi converge for I going to infinity to u1, the eigenvector that belongs to the dominant eigenvalue lambda 1. Let's introduce a bit more notation, because now it is nice that apparently those xi's that I compute, they go to u1. Now I would also like to know the value of lambda 1. So I'm interested in the eigenvalues of the matrix. So here I kind of repeated everything we had so far. So I choose a starting vector x0. I do this iteration, that's the power method. And then we have just seen in an analysis that the xi's converge to some multiple times u1. So in particular, we have that xi plus 1 is approximately this lambda 1 to the power I plus 1 beta 1 u1. And I can write this here as lambda 1 times lambda n to the power I. And that is approximately equal to lambda 1, and this here is precisely xi. So apparently xi plus 1 is approximately lambda 1 times xi. Now if you take the inner product with xi on both sides of the equation, then you can pull it out on the right side. You can divide by this thing here. And what you find is that lambda 1, so the eigenvalue, is approximately, well, this quotient here, which you can write as a times xi inner product with xi over xi inner product with itself. Now this formula is called a Rayleigh quotient. So a Rayleigh quotient, rho of x for a vector x, is defined as precisely this quotient. And you see why they are important, because if we do the power method, then apparently we can use this Rayleigh quotient to approximate the eigenvalue. So the conclusion is that if you write it as rho xi, that's precisely what it says here, that they converge to the dominant eigenvalue lambda 1. So that's a great in-between result, say. We have now found a numerical method that gives us the dominant eigenvalue, if we compute the Rayleigh quotients, plus the corresponding eigenvector, because the xi's themselves converge to u1. Here, as a kind of in-between, is a theorem that states that if you have an approximation of the eigenvector, it tells you how accurate the Rayleigh quotient is as an approximation to the eigenvalue. So let's see what we have here. So assume that we have eigenvectors of a matrix and they are normalized, so they have length 1. And assume that we have a normalized vector x, so it has length 1, 2 in the 2 norm, and say that that is some approximation to u1. Then what the theorem tells us here is if we compute the Rayleigh quotient, that's hopefully an approximation for lambda 1. And here in this inequality, it tells us how good it is. Because the difference between lambda 1 and rho is less or equal 2 times the norm of the matrix apparently, and then the difference between the vectors. So if x is a very good approximation for u1, then this norm is going to be small, and then the Rayleigh quotient is also going to be a good approximation for lambda 1. So let's see if we can prove the theorem here. So I would like to say something about the difference between lambda 1 and rho of x here. And as so often, what I do is I'll introduce a term and then use the triangle inequality. But before I do that, let's write this as lambda 1 times the inner product of ui, I think it says here, yeah, ui. Oh, it's a bit confusing because here it says ui and here it says u1. I'm sorry about that. So it just has to be u1, of course. So u1 comma u1. And that is 1. So I just wrote a complicated way. I wrote 1 here. Minus, and then the Rayleigh quotient is ax comma x. It would be divided by the inner product of x with itself, but x also has length 1. So I can forget about that. And now is the step where I said that I'm going to introduce an extra term here. So I'm going to write this as, first of all, lambda 1 times u1 can be written as a u1 u1, because u1 is the eigenvector for lambda 1. Minus, and then I'm going to add ax u1, and I'm going to do plus ax u1. So I just wrote an additional 0 there, because minus and plus, they cancel out. Minus ax comma x, absolute value. And the reason I do that is because I want to compare these two. And I can compare them because the u1 in the second argument is the same. And I also want to compare these two. I can also do that. I can grab them together because the ax here is the same. So what I'm going to do, and I'm going to do it on the next page, otherwise it gets unreadable. So let me get some more paper. So I can write that as the absolute value of a u1 minus x comma u1 plus a x comma u1 minus x. So this is just a bit of playing around here, a bit of trickery. But now what I am going to do is I'm going to move the absolute value to the separate term. So use a triangle inequality. So this is less or equal the absolute value of a u1 minus x comma u1 plus absolute value in a product of ax with u1 minus x. And then we're nearly there, because I can now say that this is less or equal the 2 norm of a u1 minus x times the 2 norm of u1, that's 1, so I'm not going to write that down, plus, and here I can write this as the 2 norm of ax, or I can give it as an upper bound, times u1 minus x 2 norm. And you see that I can write this again as being less or equal first term norm of a 2 norm times u1 minus x 2 norm plus, and this as 2 norm of the matrix A times the 2 norm of x, but that's 1, so I'm not going to write that down, times u1 minus x 2 norm. So this is the same as 2 norm of A norm of u1 minus x. And that proves the theorem. So what it tells us, so what we started with is the difference between lambda 1 and rho of x. We have found that it's less or equal to norm of A norm u1 minus x. So it tells us that if x is a very good approximation of the eigenvector u1, then this is small, and then there is the norm of A in between, but then this should also be small. So then the Rayleigh quotient is also a good approximation of the eigenvalue. Now, as we already saw in our little numerical experiment, if you do the iteration, then the xi's the components can become very big. So the 2 norm of such a vector can become very big, and it's wise always to do scaling then. So we are going to take xi divided by its norm, and then we have a new vector that has length 1, which I will call z in a second. And we get a new iteration basically, and the only thing that changes is that we introduce some scaling here. So the z's will be scaled, so z0 will have length 1. You could think of it as x0 divided by its length. Then we compute y I plus 1 as a times z. We compute the Rayleigh quotient, and that's azi with zi, and I don't have to write divided by zi comma zi in between brackets, because that is 1. So I can forget about that. AZI is called yi plus 1, so I just have to do this inner product, and that's then an approximation to the eigenvalue. And finally, I do the scaling. And I can do this iteration, and that is the power method, but now with scaling. So this is a nicer version that you will do in practice. So it's a scaled version. It's also called Rayleigh Quotient iteration. And well, we compute all the Rayleigh quotients here, so that's the reason for that. And they will converge just like the original, the first version of the power method, to lambda 1, the dominant eigenvalue. So here you see a comparison. Here we have the unscaled version, and here is, well, basically the same iteration, but then scaled. And you could wonder, is there a relation between those x's that I compute here and those z's that I compute here, and between the rows computed from the xi and the rows computed from the zi? Of course, there is a relation, and the relation is like this. So if you would start with the same starting vectors, so for x0, we also start with the vector of length 1. So what is the relation between them? Well, the relation is that zi is xi divided by these numbers here, basically to give it length 1 in every iteration step. But what is more interesting is that the Rayleigh quotients are the same. And the reason behind that is that you have the vectors both in the numerator and in the denominator, so all those scaling factors will drop out. I will prove it, but that's the idea here. So if you think back, then the Rayleigh quotient of xi is basically a xi with xi in a product over xi xi. And now if you would scale all 4 of these factors, then apparently those scaling factors, they cancel out. So let's see if we can prove that. The reason I like to do this is that if I want to look at convergence speed, I'm interested in how many iterations I should take and stuff like that, then I would much rather deal with these factors, so for the theoretical analysis, than with these ones, because you have all this scaling in between and that can be a little bit confusing. So let's see if we can prove the statement here. So I'm going to do that on a new page because I need a little bit of space for that. Now, if you look at how the vector z1 is defined, so z1, well, that is, if you look in the algorithm here, so z1, that's going to be y1 over its length, y1 over the length of y1 to give it length 1. And going back again, y1 is a applied to z null. So that is a z null over, and let's just write here the length of y1. Let's copy that. We assume that z null is the same as x0, so a x0 over that length. And this is precisely x1 over the length of y1. So let's go back to the previous slide again. What I want to show is this expression here. And I have done that now for I equal to 1. Now, the rest goes similarly. So if you would do this properly, you would use induction. Instead, I'm going to do it for z2 and then trust that you'll believe the rest. So according to the algorithm, it is y2 over the length of y2. y2 is defined as a z1. And I'm just going to copy this length of y2 here. And a z1, let's plug in what we just found here. So we have found that z1 equals x1 over y1. So I'm going to plug that in here. And then I find a x1 over length y1 over length y2. Now this length of y1, that's just a number, so I can also write this as a x1 over length y1 times length y2. And now you see we're here because a x1, that is precisely x2 over length y1 length y2. And it's all two norms here, so I hopefully wrote down all the little 2's for the 2 norm. So that is about the vector. So if you continue this, you will hopefully believe me when I write here that zi, that is xi, and then with all these scaling factors. So we have length of y1, 2 norm, length of y2, 2 norm, up to length of yi, 2 norm. So the last thing that I need to show is that it also is true for the Rayleigh quotients. And to do that, of course, I'm going to need this formula. So let's copy this whole formula here to a next slide. Copy and some more paper. And let's paste it here. And now what I would like to show is that the Rayleigh quotient, so rho zi, I want to show that it's the same as rho of xi. So the rho of zi, if you look at the algorithm, it is the dot product of yi plus 1 with zi. And yi plus 1, I can write that, if you look in the algorithm, as the length of yi plus 1 times zi plus 1, comma zi. And I can pull that length out of the inner product, so that's the length of the vector I plus 1 times the inner product zi plus 1 with zi. Zi, all the z's have length 1. So if you like that, you can also say, well, I want it to look like a proper Rayleigh quotient. So I want zi plus 1, comma zi in the numerator. And I want zi, comma zi in the denominator. And now for all the z's, I am going to plug in the equation, the formula that we had derived to get from z to x. So what we find, I just copy the length of I plus 1. And then in the numerator, I find x I plus 1 over all these lengths up to I plus 1 for the first term. Then comma, inner product of zi, and zi is the same as xi divided by y1, that should be y1, 2 norm. And then up to yi, 2 norm, divided by, and below here we have xi with this whole bunch of terms, so length y1, 2 norm up to yi, 2 norm, comma xi, same denominator, y1 to norm up to yi to norm. And what you see is that all of these norms here, so this denominator also appears here, also appears here, and it appears here, but this first term has an additional length yi plus 1, but that's cancelled out by this one. So what it says here, this is just a very long and windy way to write xi plus 1, comma, xi over xi, comma, xi, which is precisely rho of xi. So indeed, the Rayleigh quotients are the same for the scaled and the unscaled version of the power method. So if we are going to look at convergence, which will be the topic of a future video, then we can look at the unscaled version for the analysis. For the numerics, you would also always do the scaled version, but for the analysis, you can use the unscaled version of the power method. So to wrap up this video, what we have seen is how you can use the power method and then preferably the scaled one with the Rayleigh quotients and with the scaling in every step where you divide by the normative vector to compute the dominant eigenvalue lambda 1 of a matrix. So lambda 1 is the biggest one in absolute value. And we have seen how you can use Rayleigh quotient iteration to scale the power method. And we've also seen that in that iteration, the vectors are scaled. The Rayleigh quotients you find are going to be identical. So that concludes it for this video. And I hope to see you in the next video, which will be on the topic of convergence speed. So how many iterations does it take? How fast does this whole process converge? Thank you for watching, and I'll see you in the next video.